Now we're going to look at problem 946. Calculate the differential cross-section and the total cross-section for the elastic scattering of a particle from an impenetrable sphere. So remember, the differential scattering cross-section is this sigma theta, and the total cross-section is sigma, we'll use sub t, and it's integrating this differential scattering cross-section over all angles. So either we're integrating over all the scattering angles in the lab frame or all the scattering angles theta in the center of mass frame. So this is an impenetrable sphere. It has some radius. The radius of this sphere will be a. And so the potential for this will be 0 if we're farther away than this radius a, and it'll be infinite for r less than a. Okay? So we'll also be needing to use this picture that we've seen before. So what we have is the impact parameter b, and that is the distance from the center, the scattering center. Then what we have is, some particle of some size, and that's coming in and scattering off of some particle of radius a. So let's draw what that looks like. We have this radius a, we have a particle here that's going to be making it to this far away, and then it's going to be scattering away. Okay? Now note from before, what we've had is theta, little theta equals pi minus 2 capital theta. And so what that means is d little theta is equal to negative 2 d capital theta. Okay? And so this angle, here, I guess, well, this angle here is this capital theta. And this is alpha, and this is beta, and so this angle here would be little theta. To make it equivalent to the picture that we've seen before. So we also have from our notes that d little theta is plus or minus the angular momentum over r squared divided by the square root of 2 mu, the total energy minus the potential energy, minus L squared over 2 mu r squared. Right? And the potential energy when r is infinite is of course 0. And so that means that the energy is going to be the initial kinetic energy in the center of mass frame. And we also have the angular momentum is this impact parameter times this mass times u1, but we have that t naught prime is 1/2 mu u1 squared, and t naught is of course 1/2 m1 u1 squared. So make sure you know these relationships between the center of mass and the lab frame kinetic energies. So what we get is B times the square root of 2m1 T naught, and that's equal to B times the square root of 2 mu T naught prime. So now we substitute this into our equation for d theta, and d theta is equal to plus or minus 1 over r squared b and the square root of 2 mu T naught prime over the square root of 2 mu T naught prime minus u minus b squared 2 mu T naught prime divided by 2 mu r squared. This is all square rooted, but we have 2 mu here and a 2 mu here and a 2 mu here and a 2 mu here. So what we get is plus or minus b over r squared divided by the square root of 1 minus u over T naught prime minus b squared over r squared. Okay? So that gives us our d theta. What we, of course, want is a differential scattering cross-section, right? So we need to know what theta is, okay? So what we're going to have then is the potential, well, the distance is going to be here. It's going to be some infinite far distance away. It's going to come to some closest approach here, where that distance is going to be some r min, and that's going to be a, and then that's going to scatter away up to infinity, right? But this is, as we've talked about before in class, this is symmetric about these two angles. And so in order to integrate from theta initial to theta final is just going to be 2 times from here to theta final. Oops. So what that means is we have this capital theta. It's going to be integral from 0 to capital theta of d theta, and we have to use prime, is going to be, remember our relationship here, d theta equals negative 2 d capital theta, so we have negative 1/2, integral from 0 to theta d little theta prime. And so this is going to be negative 1/2 of an integral from infinity to r min, which is a, and we have plus or minus b over r squared dr over the square root of 1 minus, and the potential is of course 0, so b squared over r squared, and then we have plus r min up to infinity of plus minus b over r squared over the square root of 1 minus b squared over r squared dr. But that is going to give us -1/2 times. Now, this first integral is infinity to r min, right? We're coming in from infinity. We're going to r min. But we can flip that and flip the sign. And so what we're going to have is r min to infinity of minus plus b over r squared. Or the square root 1 minus b squared over r squared dr plus the integral from r min to infinity of plus minus b over r squared with the square root of 1 minus b squared over r squared dr. Okay. Now, we have these plus minus signs here. So we can either get them to be the same, and then that just gives us 0. And so that means that theta is equal to 0, or for some non-zero theta, for the non-trivial solution, what we get is -1/2, and then what we get is -2, the integral of r min to infinity of b over r squared over the square root of 1 minus b squared over r squared dr. And then, of course, those -2's just and the -1/2 cancel. Closest approach is, of course, going to be a. So what we get is this capital theta is going to be the integral from a to infinity of b over r squared over the square root of 1 minus b squared over r squared dr. And you can look this up in an integral table. This is a definite integral, so it's nice. It ends up being simple. The arc sine of b over a. You can, I think even Wolfram alpha will give this to you as a definite integral. Or what that means. Okay, maybe we're back. The computer that was recording this all of a sudden crashed. So I'm now going to record from my laptop, so you might hear the tap of my laptop. So what we have is sine capital theta is, of course, going to be b over a. Okay? But remember, we had capital theta, so little theta is equal to pi minus 2 capital theta. And so what we have is sine pi by 2 minus little theta by 2 is equal to b over a. And if you know your trig identities, that's cosine theta by 2, little theta by 2 is equal to b over a. Or b, which is our impact parameter, is equal to a cosine theta by 2. So remember, what we're going for is sigma theta. is equal to b over sine theta db, db by d theta. So what we have from here is db is equal to negative a by 2 sine theta by 2 theta. So we substitute that in here for our differential scattering cross section, and we get a cosine theta by 2 for b divided by sine theta, that should be a little theta, times db by d theta is going to be a by 2 sine theta by 2 d theta by d theta, so that's of course just 1. And what we'll have, this, remember, is 2 sine theta by 2. And so this will cancel out with that. And what we get is a squared divided by 4, since we have a 2 here and a 2 here. So our differential scattering cross section is a function of theta is a squared divided by 4, which we've seen before. We've seen it with the neutrons scattering off of protons. We've seen this with billiard balls. So this means that the differential scattering cross section is angle independent. And the total differential scattering cross section, or the total scattering cross section, is we integrate the differential scattering cross section over all angles, and this is in the center of mass frame, so we use d omega prime. And so this is a squared divided by 4 of 0 to 2 pi of d phi, and 0 to pi of sine theta d theta. And that, of course, gets us a squared divided by 4 times 4 pi. So the 4's cancel, and we get pi a squared. Now, if you remember when we first looked at understanding the differential scattering cross section, we said the collision of two spheres has this total differential scattering cross section. It's going to be pi b squared, because that's just going to be the area of a disk that we're scattering off of. And so in this case, the maximum impact parameter we have is going to be a. So this tells us that for our case here, we have pi a squared. And so the differential scattering cross section is going to be this total scattering cross section going into all 4 pi steradians. And so that is a squared divided by 4. So this is kind of the quick way to get to this answer by recognizing the simple geometry that we have just a sphere. But these 3 pages of math here is the full way to do it for any potential that you might be interested in.